Let's now talk about what we mean by absolute convergence and conditional convergence. In the last video, we talked about alternating series. Those are series where every other term was positive and every other term was negative. In other words, regardless of what the head of this series or sequence did, the tail, at least every other term was positive or negative. Now, if we look at something like that, we know because of what we saw with the harmonic series and the alternating harmonic series, we know that the harmonic series diverges. We proved that with the integral test. But we also were able to prove that the alternating harmonic series, where every other term is negative, actually converges. And this sort of makes sense because if some of the terms are negative compared to when all the terms are positive, then that would seem to indicate that the sequence of partial sums is approaching a smaller value, which should make it at least possible for it to converge. Now, we want to establish when it does converge, what we're going to call that, and what we'll call it when it does not converge. So when you take an alternating sequence and you've got every other term being positive, we want to think about a stronger condition called absolute convergence, where we take the absolute value of the summand and we see if that series converges. Now, we know with the alternating harmonic series that wouldn't work because the harmonic series diverges. But there are some series for which this does work. Even if it's alternating, taking the absolute value still gives you a series where it actually converges. And when that happens, we call that series absolutely convergent. And what we mean by that is we take some series where a sub n is the sequence on which it's based, and some of the a sub n could be negative, could be every other one like an alternating series, or maybe not every other one, just some of them. And we call it absolutely convergent if taking the absolute value of the summand still results in a series that converges. The sequence of partial sums approaches a finite real value. Now, we can also write it in this way with an alternating series. It doesn't have to be alternating, but again, the b sub n's are considered to be strictly non-negative, and we say it's absolutely convergent if the absolute value of this alternating series, which is the series of just b sub n, converges. Right? So we would call that absolutely convergent. And we'll see that absolute convergence is a stronger condition than conditional convergence. So now we want to take a look at this series right here, and we want to determine if it is absolutely convergent. What do we mean by absolutely convergent? By that, we mean that we want to look at the series from n equal 1 to infinity of the absolute value of negative 1 to the n plus 1 divided by n to the 4/3 power. We want the absolute value of the summand. Well, in this case, it was an alternating sequence here inside the summand. So the absolute value strips off the alternating part and leaves behind the following series from n equal 1 to infinity of 1 over n to the 4/3. Now, n, of course, starts at 1, so we know it's strictly positive, so we can drop the absolute values. Now, what do we know about 1 over n to the 4/3? That's right, it's a p series. This, in fact, is going to be a convergent p series where p is equal to 4/3. And as long as p is greater than 1, we know it converges. Convergent p series, p equal to 4/3, which is greater than 1. Now, what does that tell us? Well, we took the absolute value of the summand and we got a convergent series. And that means, therefore, the series is absolutely convergent. And that's what we say, absolutely convergent. Right? So that's the result, or that's our conclusion. Let's now talk about what it means to be conditionally convergent. if we're not absolutely convergent, we could still be conditionally convergent. Again, we're starting with some series where we have a sequence, and some of the terms of the sequence could be negative, it could be alternating, but it could be like every third one is negative, so it doesn't have to be strictly alternating. And we would call this conditionally convergent if the original series, with possibly some negative terms, does converge, but the absolute value of the summand, that series, does not converge. It diverges. So it's not absolutely convergent because the absolute value of the summand diverges, but we would still say it's conditionally convergent if at least the original series converges. And again, we can show this with an alternating series. We would say that the alternating series, -1 to the n times b to the n, where b to the n's are all positive, is conditionally convergent if this series right here diverges, the absolute value, but the original series converges. And this is what we saw with the alternating harmonic series. We know that the absolute value of it is the harmonic series, which definitely diverges. So it's not absolutely convergent, but we know that the alternating harmonic series does meet the 3 conditions of the alternating series test, so it does converge. So we say that the alternating harmonic series is conditionally convergent. Now, let's take a look at another theorem, which actually gets used quite a bit. My screen keeps scrolling around. This theorem is very simple, but it's actually very powerful. And what it says is that if you have a series that is absolutely convergent, then the smaller series, where some of the terms could be negative, must in fact also converge. So absolute convergence implies conditional convergence. So if we take the absolute value of the summand and that converges, absolute convergence, then the series without taking the absolute value must also converge, right? So this is a much stronger condition. Absolute convergence implies conditional convergence. In other words, if the absolute value converges, then it would have converged without the absolute value. The reverse is not true. We saw that with the alternating harmonic series. It's conditionally convergent, but the absolute value does not converge, right? The proof of this is an application of the comparison test, which we saw in a previous video. So we're going to start with the idea that the absolute value of the summand in the series does converge. Well, either all the terms were already positive, in which case the absolute value of a sub n is just a sub n because they were all positive anyway, or on the terms where they were negative, if I multiply that negative term by a negative, I'll get a positive. So either they're a sub n already positive, or they're the opposite of a negative a sub n, and that would make it positive. Basically, this is just the definition of the absolute value. It's either the number or it's the opposite of the number. So either the terms are a sub n or they're negative a sub n. Well, then we must know that a sub n plus its absolute value has to be less than equal to 2 times the absolute value of a sub n. Why? Well, if it was a negative value, then the absolute value of it could be negative a sub n. That's a positive value, but negative a sub n and a sub n would give me 0, so it gives me the low end. If it was actually positive and it was just a sub n, then I'd get 2 a sub n's, which would give me 2 of the absolute value. So I've got this inequality that I can write right there. And then I can use the inequality down here with the original absolutely convergent series. So I know that it was absolutely convergent. So I know that the series of the absolute value of a sub n converges. Because it converges, I can have a constant on the inside that I can take out of the series. I'm only allowed to do that if I already know it converges, but I know that this converges. That was my assumption. So 2 times the absolute value would give me a 2 on the outside times that absolutely convergent series. But by the comparison test, I can use the inequality that I have up here to say that the series of a sub n plus the absolute value of a sub n, which I know from this inequality has to be less than or equal to the series of 2 times the absolute value. And I know that this one converges because of this rule up here, then this smaller one must converge as well. That's the comparison test. The unknown series is less than or equal to a known convergent series. So the smaller one must, in fact, converge. Now, since they both converge, this series of a sub n plus the absolute value of a sub n and the absolute value of a sub n converge, then we can apply the sum and difference properties of convergent series to them. And we can actually combine these into one value. And this gives me that the series of these two minus this one turns out, of course, to be just the series of a sub n. But that must mean that it converges because it was equal to these, and these were smaller than the other one, which converged. So that must also converge by the comparison test. Since the difference of 2 convergent series must also converge, we know that the conditional one must also converge. Now let's take a look at an example and see how to apply these different rules. So we're looking at an alternating series, -1 to the n plus 1, and our summand is n over 2n cubed plus 1. So we're looking at that right now, and we want to know, does it absolutely converge, conditionally converge, or diverge? So the first thing we're going to do is we're going to look at it with the divergence test eyeballs first. So we're looking at it with the divergence test. And remember, the divergence test says that the limit of the sequence part has to go to 0. And so if I take the limit of the sequence part as n goes to infinity of n over 2n cubed plus 1, this has form infinity over infinity. You can apply L'Hopital's rule, or you can simply do the ratio of the leading coefficients, which would be 1/2, all right? Now, or rather, we give you 0. So this is going to give me the limit as n goes to infinity of 1 over 6n squared, which we know goes to 0, which means it's inconclusive, right? So basically, the divergence test didn't tell us it diverged, which is good, because we want to know if it converges absolutely or conditionally. So we've proved that the divergence test works. The next thing we want to test is absolute convergence. So we've shown that it is inconclusive by the divergence test. So it's possible that the infinite series does converge to some finite value. We want to first try to prove the strongest condition possible, which is absolute convergence. Because if we have absolute, we automatically have conditional convergence as well, or convergence of the series with the original values of the signs, the plus and the minus. So we're going to try to prove that it is absolutely convergent. So that's what we're going to try first. So we're going to take the absolute value of the summand, and this is going to give us the series from 1 to infinity of the absolute value of -1 to the n plus 1 times n over 2n cubed plus 1, which of course is just going to give us the series from n equal 1 to infinity of n over 2n cubed plus 1. So our new summand is n over 2n cubed plus 1. Now I'm not doing the alternating series test, I'm testing for absolute convergence. So I look at this one and I think to myself, I run through all the different tests I have. I've got the integral test, which I could use. but I don't want to integrate that. It doesn't look like fun. It doesn't look like something that I would enjoy doing. I also have the comparison test, which is very elegant and works really well and would work on this one as well. I have the limit comparison test, which students tend to prefer, but I can't use the alternating series test because I took the absolute value, so it's no longer alternating. So I'm going to do the limit comparison test when I'm looking at this one. So when I look at this one with the limit comparison test, I need to figure out what to compare it to. So remember, this is more or less like a rational expression. And so we ignore the +1 and we are going to compare it to a series where the summand is n over 2n cubed. So we're going to compare to the series n over 2n cubed, which of course gives me 1 over 2n squared. So let me write that down below. This would be the series 1 over 2n squared. Now I could probably also compare it to the series 1 over n squared, which of course is a convergent p series, and this is a p series as well. And we know they converge because p is 2, which is greater than 1. So we know it converges, so we know we can take out that 1/2. So I'm going to compare this one now using the limit comparison test. And remember, with the limit comparison test, you're looking for the value of rho. If rho is 0 and the known series converges, they both converge. If rho is infinity and the known series diverges, which we don't have here, then they both diverge. And if rho is a finite positive real number, then they do the same thing. Both converge or both diverge. And in this case, because we're comparing it to a convergent p series, it would definitely both converge. So we need to find rho, and remember rho is going to be the limit as n goes to infinity of the unknown sequence divided by the known sequence. So this is going to give me the limit as n goes to infinity of n over n cubed 2n cubed plus 1, that's my unknown, over my known, which I can write in either form, n over 2n cubed or 1 over 2n squared, whichever way you prefer. They both work just fine, right? So I need to evaluate this limit and see what the value of rho is. Again, this is complex, so I'm going to simplify the complex fraction by taking the denominator of the denominator and moving it into the numerator. So this is then going to give me the value of the limit as n goes to infinity of n times 2n squared divided by 2n cubed plus 1. Now I want to clean this up a little bit and simplify it algebraically. So this gives me 2n cubed in the numerator. Now there are various ways of evaluating this. There are different techniques. We've been using L'Hopital's rule a lot. And of course we can use L'Hopital's rule here as well. But there's also an algebraic technique that we can use, which is called multiply by a form of 1. And so I want to try that one here just to give you some more practice at different methods. I'm going to multiply by 1 over n cubed divided by itself, 1 over n cubed. Now that fraction is just the number 1, so I'm not changing the value of what's in the limit, but I do change the way it looks. So I multiply the numerator by 1 over n cubed, and the n cubes, of course, will cancel. And that's going to give me the limit as n goes to infinity of 2 in the numerator. In the denominator, I'm going to have to do the distributive property. So be careful about that. Remember, this gets distributed. Each term gets multiplied by the 1 over n cubed. So the first term, the n cubes cancel, and I get 2 again. But in the second term, I get 1 over n cubed times 1, which is just 1 over n cubed. Now I'm taking the limit as n goes to infinity, and I know I can pull the limit into the ratio, the limit of the numerator divided by the limit of the denominator. And I can split the limit in the denominator into the limit of the sum of the limits. And basically, 1 over n cubed as n goes to infinity is going to go to 0. So this one right here is going to go to 0, which tells me the rest of it goes to 1. Now, what was I doing again? Let's remind ourselves. We're doing the limit comparison test. We had the unknown series in the numerator, known series in the denominator. We found the value of rho is a positive finite real number, so they do the same thing. So then I need to write down my conclusion, and I'll write my conclusion here. Since the series 1 over 2n squared is a convergent p-series with p equal to 2, and rho is equal to 1, by the limit comparison test, now I want the punchline, which is the series, and I've got to remind myself what the series was again because I've lost track of it. The series n equal 1 to infinity of n over 2n cubed plus 1 must also converge. All right, so I proved that that does converge. But let's go back to the original statement of the problem. My original series wasn't the absolute value of it, it was the alternating series. And I was trying to find whether it was absolutely convergent, conditionally convergent, or divergent. And what I found is that it is absolutely convergent. So because I found that the absolute value of the summand converges by the limit comparison test, I can then say, therefore, the series, which alternates, n equal 1 to infinity, of negative 1 to the n plus 1, n over 2n cubed plus 1, is absolutely convergent. This is the strongest possible convergence condition that we have. It's the strongest possible we can make. And it means that the absolute value of the summand converges, which automatically means that this one also converges as well. So this is the conditional convergence part, but we also have absolute. Absolute implies conditional. So we know that they both are going to converge. Let's now take a look at the next example, which is example number 10. This one is rather different than any of the ones that we've done previously, because this one is not a rational expression, and it's not algebraic either, because it's got a trig function in it. And it's not alternating, because this isn't multiples, odd multiples of pi over 2. Remember, sign changes between 1 and negative 1 at pi over 2 and 3 pi over 2. So to get an alternating behavior, you'd have to have odd multiples of pi over 2, 2n minus 1 times pi over 2, or 2n plus 1 times pi over 2 inside the argument to the trig function. And we don't have that. We have sine of n. Uh-oh. Well, that looks kind of concerning, because, and remember that unless said otherwise, we assume the values are in radians, of course, not degrees. Sine of 1, it's going to take it around the unit circle various times. Sine of 1 would be positive because that would be in quadrant 1, but the sine of 2 would be in quadrant 2, so that would be negative. Sine of 3 would be, well, also negative. So I've got a problem here. I've got some positive and negative terms, but they're not alternating, right? So they are changing, but they're not strictly alternating. So let's write out a couple of these so you can see what we get. So this is the sine of 1 over 1 cubed plus the sine of 2 over 2 cubed plus the sine of 3 over 3 cubed. Let's do one more, plus the sine of 4 over 4 cubed plus dot, 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 dot. Now, sine of 1, remember pi over 2, which is the end of quadrant 1. Let's write it out over here. The end of quadrant 1 is pi over 2, which is about 1.57. So the sine of 1 is still in quadrant 1, so that's going to be a positive value. So this one's positive, right? So let's go ahead and write it in words. That's positive. Well, this is pi, and pi is about 3.14. So both the sine of 2 and the sine of 3 are in quadrant 2. They're past pi over 2, but they're not yet pi. So they're both in quadrant 2. Well, and then sine would be positive. I was thinking of cosine a second ago, so I think I said they were negative. They're not. They're both positive still. So this one is positive. This is sine, so it's the y value, and this is positive. Well, what about the sine of 4? So down here we have 3 pi over 2, which, what is 3.14 plus 1.57? That would be about 4.71 or something like that. And then coming back around here, of course, we've got about 6.28, which is about 2 pi. All right, well, sine of 4 is in quadrant 3, so it's definitely going to be negative. So this next term is negative. So the signs are changing, but they're not alternating in the way that an alternating series does. Now, the next one's going to be sine of 5 and then sine of 6. So we're going to have 3 negatives in a row, and then we're going to go back to positive, 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 then negative, negative, negative. So it is alternating, but every 3. So our question is, how do we show that this is either absolutely convergent or conditionally convergent, or maybe it diverges? So again, one of the things we want to think about is the limit of the sequence going to 0. That's the divergence test. So one of the things that we're going to do first is we're going to check that divergence test. So we take the limit, and in this case, we're going to take the sine of n over n cubed. Now, the sine of n is giving us some positives and negatives, but we know something about sine. Sine of anything is trapped between 1 and -1. So whatever this numerator is, it's a constant between 1 and -1, and the denominator is going to infinity cubed. Well, then the whole thing must be driving down towards 0. So the divergence test is inconclusive. In other words, the limit of the sequence is 0, so it's possible. All right, so the next thing we want to test is the strongest condition, which is absolute convergence. Now we're going to need the comparison test for this one because we don't have an alternating series, because they're not alternating every other one, and it's not something that we can immediately compare to something using limit comparison. We probably need the full-on comparison test. Now, what are we going to start with, and how are we going to compare it? Well, what we want to compare it to is we want to think about the trig function itself. So we want to start with the sine of n. Now, we know that that has to be trapped between -1 and 1. That's the definition of sine. You know what it looks like as it oscillates across, never goes above 1, never goes below -1. Trapping something between a number and its opposite is the same thing as saying the magnitude is less than 1, which is the same as saying the absolute value of sine of n is less than or equal to 1. So I'm trying to maybe develop and do absolute convergence here. So I've got this absolute value of sine of n is less than or equal to 1. Well, how can I develop the rest of the summand? Well, I know from my original series that n starts at 1, and I want to divide by n cubed, but I know n cubed has to be strictly positive because n is greater than 1. So you can say, so for n greater than or equal to 1, n cubed is greater than or equal to 0. In fact, it's greater than or equal to 1, which means it's strictly greater than 0. So we're going to divide both sides by n cubed. We can't have it be 0 because then we'd be dividing by 0. So what we're going to have now is we're going to have this in absolute values divided by n cubed on the left and divided by n cubed on the right. Now we know n cubed is positive, so it wouldn't matter if we put it inside the absolute value because we already know it's positive to start with. So I know that in fact, and I'm going to need probably a little more room, this must be the same thing as the sine of n over n cubed. Since n cubed is positive anyway, I could put it underneath or inside the absolute value. Well, then I have my unknown series. This is my unknown. Less than or equal to some other series. Now I know what this one is. This happens to be a convergent p series with p equal to 3. This is a known p series and it converges. P equal 3, so it converges. So I have my known convergent series larger than my unknown. So by the comparison test, it must converge. So then I simply state what I've proved. Since the series 1 over n cubed is greater than or equal to the series of absolute value sine of n over n cubed, and the series 1 over n cubed is a convergent p series, where p is equal to 3, then by the comparison test, lots of writing here, this series, absolute value of sine of n divided by n cubed, is absolutely convergent. And that is the strongest condition we have. If it's absolutely convergent, then it's also convergent without the absolute values. So we know that we have both. It's absolutely convergent and convergent as it is up here with this weird alternating sign pattern. So this is one where the signs do alternate, but not every other one as in an alternating sequence or series. So let's take a look at another example, and then we'll talk about some weird facts having to do with convergence. So now we want to look at this one right here. We have the series from n equal 1 to infinity of n times cosine of n pi over n squared plus 1. Now, you should hone in on that trig function first to determine whether the trig function is causing alternating signs or whether it's something you need to trap between -1 and 1 and use the comparison test. In this case, I know that the cosine of n pi, integer multiples of pi, are going to give me alternating 1s and -1s. So this is actually generating an alternating series. So I can rewrite this alternating series in the way that you see down here below. So when n is 1, I get the cosine of pi, so it would start with a -1. So when n is 1, -1 to the 1 would give me a negative for the first. So this series is exactly the same as this series. So I'm going to try to show the strongest condition possible, which is absolute convergence. So I'm going to take the absolute value of the summand and see what I get. So I'm testing for absolute convergence. When I do that, I end up with the series n equal 1 to infinity of n over n squared plus 1. Now, if I look at that and I'm trying to determine whether or not this converges, I think of the limit comparison test or the comparison test, where the series I want to compare it to is n over n squared. But n over n squared reduces to 1 over n, which we know is the harmonic series. So I'm going to compare this to the series, which is the harmonic series. And we know that the harmonic series diverges. So you can use the divergence test or you can use the limit comparison test, whichever one you prefer. Probably for this particular one, it would be just as easy to go ahead and do the limit comparison test. So we're going to do the limit comparison test. We're finding the value of rho, which is going to be the ratio of the unknown sequence to the known sequence as n goes to infinity. So the unknown, n over n squared plus 1, over the known, 1 over n. Then simplifying the complex fraction, we end up with n times n in the numerator over n squared plus 1, which simplifies to n squared divided by n squared plus 1. Then we can either do L'Hopital's rule a couple of times, or you can think of this as the power of the numerator and denominator are the same. They're both degree 2, so it's the ratio of the leading coefficients. Or you can multiply both of them by 1 over n squared over itself, 1 over n squared. And regardless of which method you use, you're going to find that the limit is going to go to 1. So this is going to give me 1 over 1 plus 1 over n squared. 1 over n squared goes to 0, so I get 1. Rho is 1. So by the limit comparison test, it's a positive real value. So the unknown series does what the known series does. And the known series is the harmonic series. Therefore, by the limit comparison test, I know that the series n over n squared plus 1 must also diverge. That means that the original series, so the original series, which was the sum from n equal 1 to infinity of n times cosine of n pi divided by n squared plus 1, is not absolutely convergent. So I wasn't able to show absolute convergence. Well, if I wasn't able to show absolute convergence, then I don't know that I have conditional convergence. So I'm going to have to test for conditional convergence. Now I know that this is an alternating sequence, so I can use the alternating sequence test. So what I'm going to do is I'm going to use the alternating sequence test to try to determine whether or not it's conditionally convergent. So use the alternating series test to test for conditional convergence. We know we don't have absolute, so the best we can hope for is conditional convergence. If that doesn't work, then it diverges. Okay, 3 conditions. We've already established somewhere way up here, or did we? Actually, we forgot to do it, which would be the divergence test. We need to show that the limit of the sequence is going to 0. But again, the non-alternating part, the limit of the sequence is n goes to infinity of n over n squared plus 1. We can apply L'Hopital's rule at least once. or you can multiply by 1 over n over 1 over n, and you can show that it does, in fact, go to 0. So this gives me 1 over 2n, which goes to 0, all right? So the divergence test is inconclusive, but that is the first condition for the alternating series test. Now I have to show that at some point, all the terms other than the alternating behavior are always positive, but I have that because n is always greater than or equal to 1, and n squared plus 1 is going to be positive no matter what n is, because you're squaring and then adding a positive number. So I can pass the second part, which is the n's over n squared plus 1 are always going to be strictly positive for all n greater than or equal to 1. So that's definitely true. All right, so that's my second condition. And again, there's not really anything to show there. You just kind of claim it. All right, so then I need the third condition, which is that it's got to be decreasing. So when I look at that one, I have different ways of showing it. I can show an plus 1 minus a sub n is less than 0, or I can show that an plus 1 divided by a sub n is less than 1, or I can show that the first derivative is negative. So I need to show decreasing. So that's my third condition for the alternating series test. And I have 3 ways of showing it. A sub n plus 1 minus a sub n is less than 0. A sub n plus 1 divided by a sub n is less than 1. And C, the derivative, first derivative, is negative. So you can do whichever method you prefer to do here. I'm not real sure which one would be the easiest to do. I guess I'm going to go ahead and do, well, I like the second two the most. The first one's not really my favorite. I like B and C the most. So let's go ahead and do the first derivative test. So again, my expression is n over n squared plus 1. So that's what f of n is. Again, we do not include the alternating part when we're looking at this part of it. And we need to show that this is a decreasing function. So I'm then going to take the derivative of this by applying the quotient rule. So that's the denominator multiplied by the derivative of the numerator, which is 1, minus the numerator, n, times the derivative of the denominator, which is 2n, all divided by the denominator squared. Now, we don't have to worry about the denominator part of the quotient rule because the whole thing is squared. Anything squared is not negative. So that's not going to contribute to the sign. So we really just need to focus on the numerator. So when we're focused on the numerator, we have n squared plus 1 minus n squared over, or minus 2n squared. I knew I'd lost something. So I have n squared plus 1 minus 2n squared over this strictly non-negative denominator, right? Well, the numerator then is going to give me negative n squared plus 1 over this strictly positive numerator. So the question is, ignore the denominator because it's always non-negative, and look at the numerator and ask yourself, when is this going to be negative? So we're trying to prove that it's negative. So the question is, when is negative n squared plus 1 less than 0? Well, then I can go ahead and I can move the negative n squared to the other side by adding n squared to both sides. And this means it's true when 1 is less than n squared. And then I can take the square root of both sides. Remember that n we know is strictly positive, so I can ignore the negative root. And this is going to happen whenever n is greater than 0, or greater than 1, rather. So this happens whenever n is greater than 1. So choose n equal 2. Start at 2. So, well, what about the first term, you say? Fine, chop it off, set it aside. Start at 2 and go to the back. I meet all 3 conditions starting at least n equal 2. So therefore, by the alternating series test, it is conditionally convergent. Therefore, by the alternating series test, the series, the original series, which I've lost track again of what it was, we've written it several times, n times the cosine of n pi over n squared plus 1 is conditionally convergent. So we weren't able to show absolute convergence. So then we tried conditional convergence, and we found it met the 3 conditions of the alternating series test. So we were able to show conditional convergence. Now we need to talk. We need to talk a little bit about conditional convergence and a weird fact about conditional convergence. Most of the series that we've been dealing with so far, because we've been using mostly the limit comparison test and the integral test, the terms of the sequences were mostly positive, in which case taking the absolute value doesn't change the summand at all. So most of the ones we've been studying thus far were, in fact, if they converged, absolutely convergent. But now that we have these alternating series, we're going to have some series that are not absolutely convergent, that are conditionally convergent. And there is a weird fact about these, that if you take any series that converges conditionally, you can rearrange the terms. So if you write out the terms in the sequence and you add them together in a different order, you can actually create a new series that adds up, converges to a different finite number. And you can actually get it to rewrite as a series that diverges. I'm sorry, I know this is so confusing. But it turns out if you don't have absolute convergence, then it's not really a sum in the traditional sense of the word. It's not the sum of an infinite number of terms. It's the limit of the sequence of partial sums. And rearranging those terms in a different way can create a new pattern for S sub n, the nth partial sum, which can create a new value for S infinity, which is kind of crazy. Now, there's an example of this in the OpenStax textbook, volume 2. It's on page 503. It's example 5.22, where they take the alternating harmonic series, which we know to be conditionally convergent, and they rearrange the terms in such a way that instead of adding up to the normal natural log of 2, it adds up to 3 halves times the natural log of 2. I know. How can that be? Well, because you can rearrange the terms and because it's not absolutely convergent. If we have absolute convergence, this doesn't happen. When we have absolute convergence, no matter how you rearrange the terms of the series, all rearrangements will give you the same value as the original arrangement. So this is what we've been looking at so far and what we were sort of thinking of as the sum of an infinite number of terms, an infinite sum. Well, it turns out that that idea of an infinite sum only really applies if it's absolutely convergent. Because conditional convergence, if you rearrange the terms, you can get it to go to any real number and even get it to diverge. It gives a different series, right? Which is a crazy idea. So again, this absolute convergence is far more powerful. It stops the rearrangement of terms from resulting in a different convergent value. So we really shouldn't think of conditionally convergent infinite series as infinite sums. They're not. They're the limit of the sequence of partial sums. And the bottom line, of course, is that weird things happen at infinity, particularly when it's only conditionally convergent. So again, if we have a series and we know that it's absolutely convergent, then it doesn't matter how I rearrange the term. all such series will converge and converge to the same value as the original. So I'll have a unique value for S sub infinity. If, however, it's only conditionally convergent, not absolutely, then I can either get it to converge to any real number, and I can even get it to diverge, right? So this is a weird fact about conditional convergence. I hope that this didn't just completely blow your mind. We do still have 2 tests for convergence to cover in the next 2 videos, where we'll be talking about the ratio test and the root test. The root test doesn't get used as often, but when you need it, boy, do you need it. But the ratio test gets used all the time. So it's one of our bread and butter techniques, and you're going to find that it applies in lots of different situations. It's really just a beautiful, beautiful test for the convergence of a series. I hope you'll join me for that video.